I don't know it's good or bad, but this semester, our national holidays seems to be always on Monday, not Wednesday. All right. Okay. Just kidding. Okay. Anyway, you are going to have a long weekend this coming coming Saturday, Sunday, and Monday. Okay. I wish you have a very pleasant long weekend. All right. And don't forget, we are going to have our first meeting exams, I think in 2 weeks. All right. All right. Now, to answer the question, why exact the session with an impulse? Because we want to get impulse response. Now, as I said, as we said, an impulse hammer is specialized hammers with high precision force sensor built into its tip. Okay, it has a transducers built into its tip. Now, what is its function? What is the function of impulse hammers? The answer is the tap test. The hammer's function is to excite a mechanical structure with a non-measurable input. Okay, why is the input measurable? Because I have a built-in sensor on the tip of the hammer. Okay, now this process, the process often called a tap test, works like this. The first thing you do is, of course, you have to have output measurements, which means accelerometers are attached to the structure you want to control to measure its vibration response. Okay, you want to control a structure, so you want to know its model. So you attach accelerometers to that structure. Okay, so that you can experimentally determine its output response when it is subject to the excitation of the impulse hammer. So the next thing we do after acting accelerometers to the structure I want to control, we apply the input. You strike the structure at a specific point with the impact hammers, and then you measure input. The force sensor in the hammer's tips measures the exact force profile of the impact force, which is denoted as capital F of T. This is the session input. And the session output, of course, is measured by the accelerometers. Accelerometers we attach to the structure we want to control. The goal is to apply a force that is as close as possible to a perfect direct delta impulse. This is just a full mathematical name of impulse function. Okay, so you want to use the hammer in a very skillful way. So when you strike the hammers to the structure, we hope the impact force can be very, very similar, at least as similar as possible to a impulse function. All right, okay. Now, because if you can do that, it can excite a wide range of frequency in the structures. And we will talk about this impulse response experiment in the later part of this course when we discuss frequency domain methods. All right. So now, the next thing I want to do is after tell you how to find the total response by using techniques such as convolution integral, we want to go back to the classical solution for solving differential equation. Okay, that is, these are the methods that you learn in the course of engineering mathematics. Okay, let's assume that this is the nth order time invariant system we are dealing with, where D, of course, is the differential operator. Okay, originally what I have is this. Okay, remember that Y is the output, F is the input, and Q, of course, is the characteristic equation. Now, the Y now is decoupled into two parts. The first part which is denoted as Yn of t, represent natural response. We will define natural response later. And the remaining part is what we call forced response. And we will define forced response later too. But let me remind you that forced response actually is the so-called particular solution in the course of engineering mathematics. So this is exactly what we will get. Well, why? Well, now, the next thing is that we assume this is true, and this is also true, okay? That is, Yn corresponds to the homogeneous solution of the differential equations, and Yv corresponds to the particular solution of the differential equation. Now, here, the natural response, being a linear combination, what it will look like is, it will look like a linear combination of the system characteristic modes, okay? Remember, modes look like this, where lambda is the eigenvalue or the pole of the system, the same form as that of zero input response. So on appearance, natural response look like zero input response, but they are not identical, which means they are not the same thing. They look, the appearance, they have the same appearance, but its arbitrary constants are different, okay? Okay, we will demonstrate that in the later part of this course. And for solving forced response, our engineering mathematics textbook tell us that we can use the technique called the method of undetermined coefficients, which means if the forcing function, for example, looks like this, let's say the forcing function, let's say ft is 5x times plus 7, then I assume my forced response to be also a polynomial with unknown coefficients, okay? So solving particular solution or solving for forced response now become finding the right values for A and B. We'll demonstrate how to do that by a simple example. Let's say we are interested in this solving this differential equation where y is the output and x, this is the input. X is the independent variable for these differential equations. Now, if I assume y equal to c e m t, okay, remember, in analyzing the solution, in solving a differential equation, this is always the first step. We assume the solution of this equation can be represented as this equality. This is always the first step. This assumption is always the first step. Now, by assuming C equal to C e lambda t, and then by multiplying, by substituting this assumption into this differential equation, it can be readily shown that this is what we will get. This is called the auxiliary equation, and this is also referred to as the characteristic equation of this differential equation, all right? Now, the roots of this algebraic equation is -2 minus square root of 6, and the second root is -2 plus the square root of 6. So since I assume C equal to E to MMT, and now I know the two possible values for M. So this is the natural response or natural solution for my problem, for this alternate differential equation. Noted that C1 and C2 need to be determined by using initial conditions. All right. Now, for the second part, I need to determine the solution for this part of the differential equations, which means I need to determine the force response. That is, I need to determine the particular solution. Now, based on the method of undetermined coefficients, since the right-hand side is a second-order polynomial, I assume my force response solution, that is, I assume my particular solution to be also a second-order polynomial, where the coefficients, including A, B, and C, are left to be determined. So what I do is that I take the first derivative and the second derivative of this representation, and then I substitute, plug these results back to the left-hand side of the differential equation, and this is what I will get, right? This part, QA corresponds to y double dot, all right? 4y dot result in here, which is this two, A times AX plus 4B, okay? And minus 2y appears in here with such an expression of the particular solution, YP, all right? So if this assumption is true, then this must equal to this, which is the forcing function of this differential equation, okay, which appear on the right-hand side of this equality. Now, for this two to be true, okay, the coefficients 2 here has to be the same as the coefficients of minus 2a. Same thing happened to the coefficients of x. Okay, same thing happened to the coefficients. Same thing happened to the constant part of these two representation. Here I have 6. It has to be equal to 2a plus 4b minus 2c, right? So by solving these three equalities simultaneously, I can determine the values of A, B, C to be minus 1 and minus, this is 5, minus 5 over 2 and minus 9. So my particular solution with A, B, C known can be written as this. And my total solution is this. Remember that the first part is the natural response. The second part is the force response. This is often referred to as the homogeneous solution, and this is often referred to as the particular solution, okay? Now, what's wrong with this technique? Mathematically, it can help you determine the solution of this particular differential equation without a doubt, but it has some serious limitations. The first limitation comes from the method of undetermined coefficients, okay? In setting up YP, you have to know the forcing function of the differential equation. And for the method of undetermined coefficients, these forcing functions, the type of forcing functions it can handle are very limited. It can handle constant, it can handle polynomial, it can handle sine, cosine, exponential, as well as their products. But that's it, okay? It cannot deal with, for example, log function, okay? It cannot deal with other complex functions. That's all they can do. So the forcing functions they can manage are very limited, okay? And that is one important restrictions, okay? The other thing is it decouples the solution into complementary solution or homogeneous solution and particular solution. For this part, we call it natural response. And we all know that the natural response from the solution process come from its poles, come from its eigenvalues, okay? So on appearance, its structure look like zero input response. But it does not represent the total result of initial conditions. So by using this approach, it's hard for us to distinguish which part of the response come from the input and which part of the response is the result of the initial conditions. There is no way we can do that if we solve the problem by using the classical solution approach. Now, we can, in the course of engineering mathematics, we also learned that we can solve the differential equation by using Laplace transform, okay? Now, before doing that, let's first review a technique called the partial fraction expansion, okay? Let's assume this is a transfer function of a system, okay? Now, to find its inverse Laplace transform, to find its impulse response, let me put it this way. To determine the impulse response of this system, we need to take the inverse Laplace transform of this transfer function, right? Now, to do that, you probably want to go to the Laplace transform table. But if you go to the Laplace transform table, you will see there is not such an entry for such a representation, okay? It's simply too general. So what you need to do is you have to take them apart. For example, by assuming since here, that in the denominator, what we have is x minus 1 times x minus 2 times x plus 4. So let's just assume this representation can be represented as a sum of a over x plus 1 minus 1 plus b over x minus 2, blah, 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 okay? Now, the reason why we want to do that is that you can take the input Laplace transform of these three terms easily, all right? You can check the Laplace transform table, and I guarantee you that you will find the corresponding Laplace transform, okay? Because the Laplace transform of 1 over x plus a is e to minus at ut. Remember that ut is the unit step function. So the technique of partial fraction expansion is to help us to determine the values of a and b and c. Now, how do I determine the values of these unknown coefficients? Let's combining them together again, okay? Now, to combine them, each one of them need to have the same denominators. So to do that, the first thing I do is I multiply the numerator as well as the denominator of this part by x minus 2 and x plus 4. And this is what I will get. I will do this similar thing to the second term and the third term, so that after multiplication, all these three terms will have the same denominator. And the resulting numerator look like this. And if this equality does exist, then this part has to be identical to this part. So, and this is the piece of information we used to determine A, B, and C. Okay, how do we do that? It is really not difficult. First, we have to know that this numerator has to be the same as this numerator, okay? So these two sides has to be the same. So let's just first, to determine A, let's just assume S to be 1. Because if S is equal to 1, then this term disappears. Similarly, this term will also go away. So all I left is this term associated with a, well, okay. Now, since x is assumed to be 1, x squared is 1. 6 times x is 6 plus 9. What we end up with is, of course, 16. All right? For this part, a remains to be the same. With x equal to 1, this becomes minus 1. With s equal to 1, this becomes 5. Therefore, we know that a is equal to minus 16 over 5. No big deal. Piece of cake. Now we just replicate what we have just done, okay, to determine the value of b and c by assuming the value of x to be 2 and the value of s to be minus 4. Right? Because if the value of x is minus 4, then these two terms go away. Okay, they become zeros. All you need to do is to manage these two terms by assuming x equal to minus 4 and determine c therefore become a very straightforward task. Okay, so this is the technique we call partial fractional expansion. All right. Now, as a result for this particular example, by performing partial fractional expansion to this so-called transfer function, we end up with these three first-order terms, and we can take these terms one at a time by using inverse Laplace transform, and this is what we end up with. Okay, all right. So that is a review for partial fractional expansions. Now we want to introduce pretty much it's not really not an introduction because you saw it before. Let's review Laplace transform for solving linear differential equation. Now we can do it step by step. Start with linear ordinary differential equation and its initial conditions, and then we apply Laplace transform for both sides of the equation. Okay. Now in doing that, remember to apply Laplace transform properties, especially for derivatives, and use the initial condition in the transform equation. Don't forget them. And then finally is algebraic manipulations. Solve for the resulting algebraic equation for the transform output. Then what we need to do, remember, here what we are doing is system analysis. And the goal of the system analysis is to determine the output. So naturally, in the x domain, we want to determine y of x, which is the Laplace transform of the output. And then we perform partial fraction expansion or partial fraction decomposition. The idea is very simple. To decompose a complex structure transfer function into simpler terms so we can easily perform inverse Laplace transform to obtain their time domain representation. Okay, so by using this, we can break yf's into simpler terms and then perform inverse Laplace transform to determine the output in the time domain. Okay, now an example. Here, this is our example. R is the input, Y is the output. Initial conditions are given here. R of t is assumed to be a unit step function. Okay, now by taking Laplace transform of this equation, the first term becomes this. Okay, remember that the first order term, the first order derivative disappears because it has a zero value, zero initial values. Okay, by taking the Laplace transform of these terms, this is what we have, right? And the Laplace transform of 3y is, of course, 3 times capital Y of x. And the Laplace transform of 2 times R of t is 2 times capital R of s. Okay, here, since we assume R of t is equal to 1, and we know that the Laplace transform of unit step function is 1 over x. And by knowing that y of 0 equal to 1, and by solving for y of x, this is what we will get. Note that here, this circled terms represents the results, the inference come from initial conditions. Okay? So, by rearranging this equation, these two terms which are associated with initial conditions appear here. And the impact of the input appears here. Therefore, this part, since they are the result, since this part is the result of initial conditions, so the inverse Laplace transform of this part represent zero input response. Similarly, this part is the zero state response of the system. Okay, so one distinct advantage of Laplace transform is that by tracking this solution process, by tracking the initial conditions and input functions, where do they go in the solution process? We can identify zero input and zero state response in a very straightforward manner. Okay. Now, remember that we review in the beginning of today's lecture, we review X-domain system analysis techniques, and this is what we got, right? Now here, P of X in this particular example is of course, from here you can see is of course x squared plus 4x plus 3, right? This is Q of X. And P of X in this case is of course, 2, all right? And in this case, x of x, we have unit step function, all right? So x of x is 1 over x, and r of x corresponding to here, x plus 4, okay? This corresponds to this, and this is exactly this, all right? Now, so the next thing we need to do is we need to perform partial fractional expansion. And after using the partial fraction decomposition techniques, this is what we'll get. Okay, this is for the so-called zero input response. And this is the result of applying partial fractional expansion techniques to this term, which is related to the zero state response. Okay, so the next thing we need to do is, of course, taking the inverse Laplace transform. Okay, so by taking the inverse Laplace transform of this term, this is what I will get. And by taking the inverse Laplace transform of this term, this is the result. We can do that term by term. Okay, no big deal. Okay, now remember, this is the zero input response. This is the zero state response. However, if you look at such a representation, mathematically, it is very easy to see that you can merge these two terms together. Similarly, you can combine these two terms together. Okay, so by merging these two terms together, what you will get is By merging these two together, what you will get is 1 over 2 e to minus t. Similarly, by combining these two terms into one terms, what you will get is 1 minus 1 over 6 e minus 3t. All right? Here, for this particular example, this is the natural response of systems. So natural response represent everything have to do with the pulse of the system, okay? But it does not represent the zero input response, okay? Because once you apply the input, okay, you will also excite the system. So at the output end of the system, you will have some information related to the nature of the system. So naturally, modes will also become a part of the zero-state response. After all, it is the result of the application of the input, and the input is applied to the system. And the reason why you have the output is you pass the input through the system and eventually arrive at the output end. So if the input happens to pass the system to arrive at the output end of the system, of course, the output will contain important information or important properties of the system, okay? So these terms, which are the modes, come from the modes of system, are of course a part of the zero-state response, because zero-state response is always under the influence of the system being considered, all right? But by merging those modes together, what you will get is the natural response. And the remaining term here, the only remaining term is 2 over 3, become the particular solution and or forced response, okay? But natural response, therefore, is behavior from the pulse. It gets contribution from both the initial condition and the input itself, okay? This part is component condition. This part is come from the input, all right? Forced response, the forced response is not the entire response due to input. Don't mix forced response with zero input response. They are not the same thing, okay? Because forced response is not the entire response due to the input. It is part of the response that is directly caused by the input and has the same form as the external input. Here, because my input is what? Is a constant, right? So my output, the forced response, is also a constant. If my input is a polynomial based on the method of undetermined coefficients, I'm 100% sure my output will also be a polynomial. They have the same form as the external input. This is implied in the method of undetermined coefficients. Okay, now the reason why I want to review the classical methods for solving differential equations, which I think you probably have learned in the course of engineering mathematics, is because the reason why I want to do that is I want to tell you natural response and forced response, that these terms can be misleading. You probably will think forced response represent the overall result of input, but it is not the case. Similarly, you probably will think and natural response represent the overall contribution from the initial values, non-zero initial conditions. That is also not true. You really want to know who has done what on the system. You really have to go to the zero input, zero state response approach to distinguish the inference of initial condition and the contribution of the input. And that such a distinction is important because in control, we can only take care of zero state response. There is nothing we can do without the zero input response. All right. Okay. Now, let me give you another examples to help us understand impulse, zero input, and zero state responses. Here, again, we are dealing with a second order differential equation. By taking Laplace transform of this equation and by assuming all the initial conditions are zeros, I sincerely hope you that you can find this result without any difficulty. This result of Laplace transform at this time should look very, very natural to you. All right? Just go directly from here to here, one term at a time, without any difficulty. All right? Here, of course, capital Y and capital X are the Laplace transforms of the output and input, respectively. Okay? By manipulating this algebraic equation to solve for Y, this is what we will get. And what we really care about is the mathematical model of this system in the X domain, which is transfer function, which is defined as the output of the Laplace transform of the output to the Laplace transform of the input. Okay, I repeat this statement many, many times. Okay, so after so many times, I hope you has memorized this. Okay, so this is the transfer function for this system. Okay, now by using partial fraction expansion techniques, I can rapidly determine that h of x, which is this, can be decoupled, break into two terms. And by taking inverse Laplace transform one term at a time, this is what we'll get. Okay, remember what is h of x? H of x is the transfer function. Therefore, its inverse Laplace transform has to be the impulse response of this system. Okay, so how do you, next time when I ask you to determine impulse response, how do you do that? Piece of cake. Okay, find the transfer function, apply partial fraction expansion if necessary, and then perform the inverse Laplace transform. That's it. Okay. Now, by using Laplace transform, finding impulse response is a very straightforward process. But finding impulse response in the time domain without the use of Laplace transform is not that easy, right? Finding the impulse, that is finding the solution of a differential equation when the input is an impulse function, is not that straightforward. Okay, at least you cannot do it by using the method of undetermined coefficients. All right. Now, the next thing I want to do is we are still dealing with the same system. Okay. But here we have initial values. The first thing I want to do is to determine a zero state response. The first step, of course, is assume that zero state response can be represented as C times e to lambda t, where lambda is the eigenvalue, or lambda is the pole of the system, and e lambda t represent the mode of the system. I repeat what I just said already many, many times. Okay. Now the characteristic equation can be written as Q of lambda equal to 0. In this particular case, it can be easily shown that based on this differential equation, we have this characteristic equation. Okay, lambda squared plus 3 lambda plus 2, and it can be easily shown that this is actually a product of lambda plus 1 and lambda plus 2. So the eigenvalue is, of course, -1 and -2. So my zero input response is this, okay? It's the linear combination of these two modes, all right? This is my zero input response. Okay, the next thing I want to do is I need to determine this unknown coefficients. So I need additional conditions to help me to do that. These required additional conditions come from the initial values. I know that my zero input response is this, all right? So I also know the initial value of y is 0. So by setting t equal to 0, this equality can be rewritten as this. This becomes C1. This becomes C2 when t equal to 0, right? So this is the first equality which can help me to determine the values of C1 and C2. And then the next thing I do is I use this piece of information. Let me first take the derivative on this representation, and this is what I will get, all right? Now, then by setting t equal to 0, this is what I will get. So here I have two conditions and two unknowns. By solving these two conditions, this equation, linear algebra equations, simultaneously, it can be easily shown that C equal to 5 and C1 minus equals to minus 5. So therefore, this is my zero input response. Okay, this is the zero input response. Okay, here, hopefully, by solving here, hopefully you understand the role of initial conditions. Hopefully you understand the role of initial conditions. Here, because with these initial conditions, you can actually determine the unknown coefficients associated with the zero input response. Okay? Now, remember, their initial conditions has nothing to do with their state response. So we use the information provided by initial conditions to determine their input response. Okay, now the next step I want to do in order to find the total solution, after finding the zero input response, I need to determine the zero state response. Now, in this particular case, I assume the input to be e to minus 3t, all right? And then again, I take the Laplace transform on this equation. I know that this is what I will get. Actually, we did this before. The only difference is that we didn't know what x is. Now, since x of t is now specified as e to minus 3t, by taking Laplace transform of this expression, this is what we will get. Now by plugging this representation into here, we know that y of x, since it is equal to h of x times x of x, therefore we know y of x to be this. And then with this representation, and then we perform the partial fractional expansion to decouple y of x into three simpler terms, three first-order terms. And then we take the inverse Laplace transform term by terms. And then finally, we determine the zero state response. And remember that the total response is the sum of zero input response and zero state response. So we simply add them together. Again, you find that you can merge this term with this. Similarly, you can merge this, you can merge these terms with this, right? So after merging these two terms together and merging these two terms together, this is what you will get. This is the natural response. And the resulting term, the only remaining term, the only remaining term is this. It's forced response, also called the particular solution. Okay, now, how do I come up with such a solution? I cannot do it by myself. I simply get ChatGPT this equation and tell him, these are my initial conditions. This is my equation. This is the corresponding initial conditions. Please solve please find the zero input response and zero state response for me. And all the materials given here are actually provided by ChatGPT. All right. So large language model, nowadays, large language model is already very powerful. He can actually solve their input response for you. So if you don't understand how their input response works, you can go to ChatGPT to ask it to help you. Okay. Now, after going through this process, I hope you understand how to find their input and their state response by yourself. I urge you strongly, practice it, okay? Find yourself an ordinary differential equation. Ask ChatGPT to solve it for you, but you also have to solve it by yourself, by hand. Because during the exam, I probably will ask you to do that, and you to do it by yourself. Okay. Only doing it by yourself, you can really understand what is really going on. Otherwise, we will always be a slave of AI, and that's not what we want. All right. Okay. Again, a simple example. This is the transfer function of a system. This is the input. This is the output. Okay. Now, if you want to find a natural response and forced response, always remember natural response are associated with pulse, and forced response is associated with the input. It has the same mathematical structure as the input. All right. So that's, again, is what I want you to know about natural and forced response. Now, let's switch our gear. In addition to decoupling total response into zero input and zero state response, we can also decouple the total response into two different components, transient response and steady state response. As implied by these figures, okay, transient response represents short-term behaviors, okay? It will decay over time, all right? Now, steady state response, by comparison, is the remaining part of the total response. That is, if you remove transient response from the total response, what is left is nothing but the steady state response, okay? Now, let's check out an example to help us understand the difference between transient and a steady state response. This is the second order differential equation that we are interested in. This is its forcing function, okay? And initial conditions are also given here, okay? Now, by using the technique we just have reviewed, you can easily find its complementary solution or natural response as this. And you can then find its particular solution as this. This is the natural response. This is the forced response. Okay? Now, here, this part is, of course, the transient response. Why? Because of these terms, this part of the response will vanish as time approaches infinity. By contrast, this part of this response, they are made of sinusoidal signals. And you know sinusoidal signal always have a oscillatory pattern. And that oscillatory pattern will never change. So it won't die out. And it become a part of steady state response. Okay? Okay, it's 11 o'clock. Let's take a 10 minutes break. Yes, any question?